Hey, what's up? Last night I was trying to figure out how many different combinations of words there were that were legal in Wordle. How many, pairs of three that covered every single vowel. And apparently, this is a harder problem than I thought. So let's take a look at this again. So I load the valid words in, right? And then I just have some checks just to make sure that everything's good. And then I only wanted words that were all unique letters, no repeated letters. So I got rid of things that didn't. Um, yeah, I think this is a good starting point. So I don't remember what that was for, and I don't remember what it stood for. So, okay. So 9,365, right? So I'm just curious if we naively looked at every combination of three, what would that be? That would be, oh God, I think I'm starting to see the problem. So 821,340,000,000. You get the point. It's a lot. There's a lot of combinations. Okay. Now, I think that what we can do is we can build some sort of a tree over whether a word has a number or not. I think. I I think. Okay, so does it matter what order we go in? It seems like we would want to branch from the vowels early on. Yeah. Okay. So the bit values, I've gotten rid of the bit values. So I guess we'll do that. So A, E, I, O, U. Um, Letters, vowels first. Is this right? um, Assert length of vowels first equals length set of vowels first, and length of let's vowels first equals 26. I probably missed something. Oh, no, it worked. Okay, that's cool. Yeah, A, E, I, O, U. And you know what? I wanted to include Y also, so that's what I should have done. I should have just typed out all the letters and then moved them. Oh well, whatever. And I think actually E before A. And I think EA is the most common combination of vowels. So let's figure this out. So we're going to have bit value equals a dictionary, and then we'll say for I, comma, letter, and enumerate, and then bit value equals 1 I, like that. Let's just see what that looks like. I'm sure that it's fine, but I just like to see what I'm doing. Okay, so E is 1, 2 is A, 4 is I. Okay, yeah, that's exactly what I wanted. So we're going to say bit value of, oh, we can't have two bit values, can we? Letter mapping. That's probably what PM stood for, bit mapping. Okay, letter mapping of letter equals bit value. That makes sense to me. So yeah, for each word is going to be assigned a number, and then we're going to put them into a tree. And I'm hoping that this tree is going to help us. So let's say class tree node, T node, tree. Maybe I need more coffee. Yeah. So let's say, do we need words? Do we need words? I don't know. Maybe we need words. Maybe we don't need words. I don't know. Count with children equals 0. Stop adding vowel. Okay, words, count with children, and then, well, just children, I guess, equals default dict of tree node. I didn't have to import it, or did it automatically? Oh, that's cool. All right. Okay. And then I think that we are going to load these based on the existing ordering of letters from, where is it? Letter mapping, like that, right? And yeah. We can do this. So add word to tree, root, word, like that. And you know what? I think that we should pre-compute the word value. Word value. I don't think that that should be inside of this. Okay. So what we're going to do is we are going to say for I in range 20, not 25, 26, bit mask of current. Did I use that already? I feel like I typed that already. No, I had bit value. Okay, so bit mask equals 1i, like that. And then we need to know if it has the word or not. Can I access this, or is this global? There we go. Now I can access it. Then letter equals, wait, this is stupid. I have the word value. I have the word value. What am I doing? Okay, so, and word value. I mean, basically, those are the only two choices. Does it really make sense to have a dictionary, though, if all we're saying is has letter, doesn't have letter? I don't think it does. Has letter equals tree node. You know what? Having the default dictionary allows it to dynamically instantiate. So maybe there's a little bit of overhead, but I'm not too worried about it. So root. So current node equals root, right? And then we're going to say current node equals current node children of bit mask. Yeah. And that should get us to the end. That's pretty simple here. There's no recursion. And then it's simply current node pens word, comma, word value, like that. Because we have to save the word value somewhere. Okay. So let's see how quickly this loads. I don't think it should be that bad. For word in, well, words unique. We're going to say add root equals tree node. Sum of I for I in word, and then it's simply going to be BV of I, right? Bit value. Is that not what I did? There we go. So let's see how long this takes. So st equals time dot time, and then en equals time dot time, and then print, yeah, seconds elapsed. Cool. Let's see if we can load it. But I never thought loading was the problem. I always thought searching was the problem. All right. Now let's gather the counts. Gather counts node. So, yeah. Current node. Okay, now first off, it should. I want to check the integrity of the tree. So assert node dot words equals is not equal to node dot. God, okay. When it's helpful, it's helpful. When it's giving me bullshit advice, that's a problem. Children. Length of node dot children equals 0. Right, and then that should verify. Yeah. So if node dot words, then return length of node dot words. Right? Well, two things. We'll say node dot count with children equals length of node dot words, and then we can return this directly. Right? Otherwise, node dot count with children. Well, we'll do it for all. 4k comma v in items. Yeah. And it's simply going to be gather counts of v. Node.count with children. Okay. Yeah, there we go. So that should get all of them. Okay. So let's gather the counts on the root, and then I am curious. Print root dot count with children, and then let's just see root dot children 0 0. So how many words do not have either an A or an E, right? Int and none type. Something is wrong. Something is wrong. Okay. Count with children. How? How? We initialize this, and this is a default dict. So even if there isn't anything in it, how the hell can we have a null? Now this is interesting. It's saying that this is null, but this passed, right? Gather counts. And we populated it too. What in the hell? Okay, something weird is going on here. Int and none type. Gather count. Oh, God. No, 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 that's fine. All right. How did it speed up? But you know what? I don't even care. Whatever. It probably cached the file or something. That's fine. It's not that weird. So, did it just say that there's 9,365 words? Yeah, that's probably a problem. How many words were there supposed to be? There were more words than that, right? There were like 12,000. Yes, but there weren't 12,000. Okay, no, that's right. That's right. It worked, and I'm just being stupid. Okay. So, let's see here. So, 2,048. Now, this is good. This is good. We can calculate how many combinations of words from this directly, right? So every combination, trying to think. Okay, so for I in range 2 to the 5th, right? So that's every bit. Here, I want to see this. I don't do that. Two to the 5th, right? And then okay, so through 31. So I, J, K. This will be the distribution of bits in the 3, and then we can simply force them to be ordered. J plus 1, like this, and then we make sure that none of them share any bits, right? So if I or J or K dot bit count does not equal 5, then continue. Need all the bits. And then if anything is shared, so if I and J doesn't equal 0, or I and K doesn't equal 0, or J and K doesn't equal 0, then continue. Share no bits, right? And that should give us a unique mapping of all of the different vowel combinations that touch all 5 of them. And then I'm curious how many combinations there are. CNT plus equals 1. And we will see CNT, comma, combinations. Yes, go away. 40 combinations. Okay, yeah, I can buy that. That makes sense. All right, so let's let's try to figure it out. Okay. So has these and only these, right? That's what we want to know. Should we use recursion? I don't think so. Fetch vowel combinations. And it's simply going to be root, comma, value, I guess. Value. Okay. For I in range 5, bit value equals 1 to the I, and then n equals root, and we are simply going to say n equals n dot children of BV and value, like that. And we probably just want to return a node, right? Return n to the node. Yeah, so let's see. This is how many combinations, but then we need to know how many specific... this is just a count of the true combinations. I don't know what the hell I'm talking about. True combinations equals 0. And we will say that this is fetch vowel combinations of root, comma, I times J and K, and this is the true combinations plus equals, and this should be the number that I was trying to get last night. Print true combinations. Tree node and tree node. Oh. Okay, count the children. Count the children. Count the children. And run. All right, so 2,470,196,729. Yeah, it's probably no surprise that me attempting to find every combination in a loop was going to be slow, because it didn't matter how I organized it. If there truly are that many, then yeah, that takes a while. And this is much faster. So what I want is my best first guess at Wordle should be something in one of these pairs. Right? In other words, some of these pairs are not valid. Okay. Number this time equals that, and yeah, number this time. If number this time equals 0, then print I, J, K. Exactly one. Exactly one. Um, so you can't have no vowels and then you can't have zero vowels and just an I and then somehow get all the rest of the vowels in the last step. That's kind of funny to me. I don't think we want to consider things that have no vowels at all. I am kind of curious though. Like, is that how many words have no vowels? Print number of words with no vowels. I'm curious. I'm curious. And then this is going to be 0. Um, 25 words with no vowels. N equals. Okay. Deaf, dump all children, N. Yeah, so if N dot words, then for word, comma, value in N dot words, print word. Otherwise, 4K, comma, V, and dump all children, V. Yes, thank you. Autocomplete did not fail me that time. What are these 25 words with no vowels? A. Not root. And Birals chinned crypt. Oh, that's a real word. Lynch, that's a real word. Psych, that's a real word. Okay. So they all have a Y in them. Is there one that doesn't have a Y? CRWTH. That may actually be the worst guess in Wordle. I mean, that's just downright impressive there. What that means. Now, I'm curious if 27, I'm sure 4 appears. So let's see. All numbers equals set. Number this time. If it doesn't equal 0, then just all numbers dot. God. Okay. I, J, K. Right. And then print length of all numbers and list of sorted of all numbers. And I think what it's going to say is it's going to say everything other than 0 is valid, right? 30. Oh, well, wait a minute. Oh, so there is a way to do it as long as you don't choose I for the second letter. Fascinating. Well, regardless, I don't think that we are going to be including 0 in this list of things here. But what's the other one missing? There's no 31. So there's nothing that includes every vowel. And what is the other missing one? There is no other missing one. I think that for our purposes, we can start this at 1. Because, well, Do we want to include y? Of course we want to include y. What kind of question is that? That's why we put y at the beginning, right? So this should be always include that and 2 to the 6th, 2 to the 6th, 2 to the 6th. Bit count has to equal 6. There can be nothing shared. And then this goes to the 6th. And there should be even more combinations. We are now counting y as a vowel. All right, number of words with no vowels. Well, I kind of excluded. We sort of made that invalid. So yeah. Yeah, number of combinations is 957 million. Did it go down? That's interesting. If we insist on there being a y in our set, it doesn't increase, but rather decreases the number of combinations. However, I do think that y is a valid guess. So I am only interested in words which appear in one of these, which I just realized doesn't actually cut it down at all. Okay, so print length of true combinations and list of sorted of true combinations. And why are you angry? Length of true combinations and list of sorted of true combinations. I didn't want true combinations. I wanted all numbers. 52. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's basically every word. It's basically every word. Right? I mean, yeah, maybe there are some numbers missing, like 27 and 31, but that's because those words don't exist, not because we're making a meaningful reduction in the search space for the best guess. Okay, I gotta think about this. I mean, I generated the number of combinations, but at the end of the day, we're looking at everything. But we could probably include, just a list of pairings. So if we had pairs of nodes, yeah. Well, what is the number of pairs of choices? It doesn't matter because we're not looking. I said pairs. I meant triplicate. We're not looking at a triplicate pair. We're just looking for the best first example. I still want to know what it is, though. Didn't mean to hit debug. There's just 90, which is that's not that bad. Okay. Well, if I've had this much trouble, so for any given word, it would traverse a given path, right? Obviously. And then that path could either match things yellow or green or gray. And green is actually harder. find. So it almost seems like we need an alternate tree structure of what the location of the character in the word was. And then if we passed it, we can't do that though. We can't run every word. It doesn't matter if it's in a tree. We can't run every input word against every possible output word. That is the n squared problem. But is n squared a problem for n cubed is a problem? I don't think n squared is a problem. Well, let's find it out. Let's figure this out. Okay, so we'll say en equals time dot time print elapsed time en, and then let's see what let's see. Okay, so for I in range length, we just need all words. For j in range I plus 1, comma, length words, so word 1 equals, and then word 2 equals that. We want to know how many shared numbers there are. In other words, we want to do some kind of a calculation on it. Let's reset the time here so that I can look. Maybe the problem was the triplicate from the beginning. Okay, so start end time, and then we're going to have set 1 equals set of W1. Let's not do that. C1 equals counter of W1, and then C2 equals counter of W2, and you'll have shared numbers equals 0. Yeah, and then for k comma v in c1 dot items if c in c2, then shared numbers plus equals min of, well, v comma c2 of k, right? And then I'd like to just know that we did something, and let's see how long this takes. Maybe it's not as bad as I think. Okay, can we do something on all of the words n squared? I'm going to get coffee and see if this finishes. All right, so we... what is that? A little over 3 minutes. Just long enough to be annoying. So I did realize something. Okay. This would be the word we are trying against, right? And then this would be the word we are potentially matching, right? And, okay, let's figure it out. So for this, there would be a yellow count and a green count, right? Yeah, so for, I don't know, x comma y in zip w1, w2, if x equals y, then green count plus equals 1, right? And then I don't know. Let's do W, no, not like that. 4x in W1, because remember, these are unique. These are unique. We say if x in C2, not x2, in C2, then yellow count plus equals 1, and then we have yellow count minus equals green count, right? And you could probably start a heuristic right there. But I want to know what's actually the best word rather than, approximating what the best word is. Presumably a green, just in general. I mean, this is just off the top of my head, would be like 5 times better than a yellow, or I don't know, maybe 4 point something times better than a yellow. Yeah. Now I don't know. Interesting. Interesting. Well, we know for a fact that we cannot now iterate over every single word. That is just a complete non-starter. But we can filter down based on which letters are present or not present, at least at the top level, right? Well, we don't know. There's explicitly not there, and then there is let's just see. Let's just see. Because if we have a green, this would be so much easier if it were just if it's there or not, rather than if it's there, but it's not green. But maybe if we pre-sort it. Well, yeah, but I mean, some of these, like, sometimes you guess and you don't get a single letter in response. Not one single letter. Wait a minute. But if there's not one single letter, then there's not one single green. Ah. Okay, fine. What if you got 1 green and 4 grays? That could still be thousands and thousands of words. Are we going to look at thousands of words for what had a green A? That doesn't make any sense. We need to filter on the greens first. It's the only thing that makes sense. And yes, it would be. It would be at most 1, because that's how we're doing it. We have to build another tree. We have to build another tree. There's no way around it. So this is a harder problem than I thought. All right. Add word to tree. Okay, I think that we should do like before. But we just have to take into consideration the position. We're gonna do yellow. Yellow is any position. No, that's stupid. We're rebuilding the damn tree. Right? We're going to come down here. We're going to say tree node green, I guess. Okay. And what we had before was tree node yellow. What did we put into the tree node? Words unique. It needs to be words. Okay. Root green equals tree node green. So yes, it will be words. And then it will be, I'm less concerned about count with children. Am I? No, I'm not. Okay, deaf children equals default dict. Okay, so the choices are going to be none of this letter or one green somewhere, right? And there has to be an option for none. And I guess we could we could define none as 5. But what if a word has a double letter? Then it'll have to branch. If it appears twice, then it will have to branch. But if it branches, then we can't naively add it. Ah, shit, you're right. You're right. Well, that's kind of a pain in the ass, isn't it? Okay. Let's get rid of count with children. And we have to know that there could be duplicates. So children is default dict of tree node. And none of this letter is position 5. Right? Add word to tree. Add word to green tree. Root. Word. So it's going to be letter. This is absolutely going to have to branch. Yeah. Character index. If character index is greater than z, then we're done, right? Then simply node dot words. Would it be more than one? It would if we're defining none of this. No, because there has to be green somewhere. There's only one word. There's only one word. If we've defined exact positions, node.word equals word. Simple as that. Otherwise, oh, guess it's time to wake up. That was quite late. Okay. Otherwise, we have to split, and we might have to split multiple ways. So, character index. So, if char index not in word, that is trivial, then it will simply be add word to green tree. I really wish it didn't. That's not helping me, it's just confusing me. I'm expecting it to not be a strongly typed language. Is there a way to turn that off? Whatever. So node dot children 5 word never changes, and then this is going to be CHR of 1 plus ORD of character index, right? Yeah. We recurse. Otherwise, for I, well, in range 5, if word of I equals character, what the character index, there, and it's now appearing. It's now appearing multiple times. So there we go. I don't know how crazy that's going to be. I mean, I guess it's just every duplicated letter means that it will have an extra node. The worst it could possibly be is 5 times the number of words that there are, which is just not that crazy. So add word to, that's it. That's all we have to do. Yeah, I'm total final node insertion equals 0, and then this definitely needs a no. Total final node insertion plus equals 1. And then let's see, print total final word insertion. Comment this out. Let's see how long it takes to populate this and how many nodes we get. Elapsed time, that was fast. For W in words. Add word to green tree, root green W, character index. No, it should be lowercase a. All right, run it. Oh, you know what? That's not even that bad. Oh, I thought it was going to be much worse than that. Okay. And it goes pretty damn fast. So we want to know, based on this, you know what? There's not going to be duplicates if we go down the tree. There won't be. So there's going to be a bit exclusion, and there's going to be a bit inclusion, and then there's going to be a don't know, right? And the don't know is whatever's left. That's when we have to recurse everywhere. Characters anywhere, characters in specific spots, and that how would I know which character was in which spot? I mean, I just have to pass the word down. That's the only way that I'm going to know. So, yeah. Hey, I turned you off. Actually, I probably snoozed it. But I want to claim that it's not my fault. Okay, so let's see here. Okay, so we're going to find now every single word pairing is going to be the same probability, which means that we can naively add them together and we don't have to divide by the number of different combinations that there are. We can just compare the numbers to each other directly, and if one scalar is higher, we don't care what unit it is, then we say that that's a worst case. And then the proportion of those numbers will tell us, all right, if you guess this word, here's the number of remaining words that it could be based on the results that could come back based on it being any word inside of the inventory, right? And if you wanted to cheat, you could have this apply against the actual words that are in the actual database for future guesses. I think that that's shitty. I don't think I should do that. I mean, if you're going to cheat, why not just look up what the answer is going to be, you know? We have to treat the problem as though the daily guess is random. If we seed our problem with knowing what the daily guess is going to be, then that's cheating. That's stupid. And just because, there's like a layer of abstraction, there's no point. Okay, so this would be the word we're trying against. This would be the word we are potentially matching. Yellow count, green count, and this takes like 3 minutes, right? 3. Now the question is, there's 3 states for every cell there, right? And it seems like we're doing a little bit of circular logic. We're going to say, if it was this, then was it this? When in reality, we could just look at greens and yellows directly. Stop doing that. Python console. So there's 5 cells, and there are 3 states for each cell, right? Which is 243 different combinations. Which is certainly less than 10,000, and it doesn't require doing all of this bullshit math. Well, this is what made us not require the proportionality, though. If we switch it, then we're going to have to say, okay, this is how good this combination is, and this is how frequent this combination is. And it's sort of inversely proportional. Well, we have to do something. So, let's see here. How the hell are we going to do this? Seems like every time I want like a different base counter, I have this same problem. For I okay, trying to think here. For ARR in I1 in range 3. 1, 2, 3, 4, 5, right? 1, 2, 3, 4. You know what? I should do 0 through 4. I'm positive there's a better way to do this. I0, I1, I2, I3, I4. ARRS equals that. We don't recalibrate it or calculate it every time. And then I think that we actually, so let's say J, J, J. No, this is stupid. This is stupid. Stop being stupid. Okay. So for each of these, we should be able to calculate a number of possibilities, right? So we're saying for this letter, and this is only going to work if every character in Words Unique is indeed unique, which we're assuming that it is. So we want to know, likelihood that it will happen. How good is it? And I think that they're the same number. If the likelihood of it happening is precisely 1, then that's very, very, very rare. But it's also very, very, very good, right? Whereas, let's say worst case scenario is it's every word in circulation, then that would happen very, very frequently, and it would be very, very bad. I think it's n squared. I think the higher the number is, you just add n squared. So it's the number of choices. I think it's as simple as that. Okay. So now we have to figure out what the probability is for this combination. So find number of combos, right? Node character index. Error. Oh my God. Now you don't have to worry about duplicates in this circumstance, right? So character index. Yeah. All right. So I don't think that we should traverse if it's not already there. Well, obviously. Okay. If node, no, where's our definition? If node.word is, do we say equal none or is none? It auto-filled the wrong thing. And length of node.children equals 0, then simply return 0. There's no reason for us to proceed. Yeah. Which means this path has something. So ARR character index. Oh, this is not ideal. Oh, shit. Okay, I figure out what I need, and then I figure out how to make it available. So, let's just code it anyway, and then we can worry about optimizing it later. So, if character index not in, where the hell is word? So far off to a bad start. If it's not in word, then what? then return, let's see, find number of combos, node children, 5-word ARR, and then this. Trivial. When in doubt, recurse. All right. Okay, sorry. Friend invited me to lunch. I want to ignore. Sometimes, like, an entire conversation is going on. It's like, well, fine. If you don't want to go to lunch with me, then fine. It's like, no, I was doing a stupid YouTube video. Okay. All right. So if it's not in the word, then that. If it is in the word, then we need to know what it is. So we need to get the index of it. And then we need to know, is it yellow or is it, so index of char equals word dot, is that? Concrete subclasses. Just tell me what it does. Oh my god. Hello dot index e. Oh. Okay. That is what I thought. It was fine, but index is fine. That's fine. So index of char and then state of char equals. Now hold on. We're giving ourselves a circular argument here. This should define the state of the char. No, because if it's not in the word, then it's irrelevant. Right? Oh, I did do this wrong. If the character is not in the word, then we need to return everything. 4k comma v in, no, we don't need that. 4v in node dot children dot values, and then s equals 0, s plus equals find number of combos, and then this is going to be v, obviously. Yeah. No statement of inclusion or exclusion. So this is when it explodes. And then just return s. So this is our number. Now, if it is in the word, so character index in word, and then we are saying, so either green or yellow, not gray. It's either green or yellow and at a given position and only appearing once. Assert character index in word and word dot count character index equals 1. I know that that's wasteful, but if I came back and passed the wrong value, then this method would absolutely blow up. So I'm fine with a few milliseconds here. So okay, index of character equals word dot index of character index, and then state of char equals well, ARR of index of char, and then this is 0 is gray, 1 is yellow, and 2 is green, right? So let's handle each of them. So if state of char equals 2, if state of char equals 2, then it's green. Then it is simply return find number of children, and then this is going to be node dot children of index of char. This is the best case scenario, right? Yeah. And then if state of char equals 0, then this is the worst case scenario. So this is going to be, it was in the word, but it doesn't exist here. No, you know what? You know what? That's fine. That's fine. That's fine. That's fine. Because this is not the worst case scenario. Node dot children of 5. So at this exact letter at this exact position, right? And then this is going to be this exact letter exists nowhere. Now, this is counterintuitive, but a yellow is actually the worst case scenario. So it's going to be 4i in range 5, not 6, mind you. So s equals 0. And then s plus equals find number of combos node dot children of I word return s. And that should be every combination. Return, return, return. I don't need an assert that it returned. It did. There's no way to get out of here without returning. Okay, so the number of combinations is here. All right. Well, I do hope she picks a good place to eat. Okay. So is it going to work? Have I screwed it up? All right. So every word is going to have an associated cost. Okay, so for ARR, cost this word equals 0. Word equals words unique of I. ARR, and then it's going to be cost this word equals find number of combos, root word, ARR, not that, squared. Yeah. Cost this word plus equals. So for every choice, we figure out what the probability is, and then why is this angry? Member of none event. It shouldn't return none. 0. It's just being stupid. Okay. All right. And then So best score equals, I don't know, 25,000. 10 to the 27th. I don't know. And then best word equals none. So if cost this word is not is less than, then best word equals word and best score equals cost this word. That sounds excellent. Okay. Sorry. I promise I'll stop looking at my phone. This is just going on longer than I expected. So best word. There's no way this is going to work. Print best word. Tree node object has no attribute word. Did you mean words? I don't want a tree node. Root green. Oh. Whoopsie. I'm gonna put that down to a whoopsie. Okay. Oh God. Okay. What is the error? Character index in word and word count. No. No, 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 no. That was very wrong. Substring not found. What? Okay. State of character. Oh my God. This should be handled up here. If character index. This was right. If character index is not in Word, then we return something. But this was indented, so it was messed up. Okay, I get it. Hey, my assertion helped. I thought my assertion was making my life bad, but it made my life better. All right, sounds like I'm getting lobster for lunch. I have no idea how long this is going to take. I mean, I thought with it being a tree that it would be faster. Everybody's a tree. I just thought of the Captain Planet parody thing. Sorry. Okay. I guess this could be pretty time intensive. All right. Look at my loop that calls what is the complexity of this? Seems to be taking forever. I don't want it to make any changes, so ask. All right. This is kind of draining my energy. This is taking way too long. If it's going to give me my answer, then fine. But if it's going to run for 10 hours, you know, that's not fine. I just realized if the n squared loop was taking, let's just say 3 minutes, and there's 10,000 words, 30,000 minutes would have been... It's okay, so it would have run in less than 2 weeks, right? Let me look at the actual data slices to give you concrete numbers. All right. Okay, that's thinking. Let me kill that runaway shell and count more simply with Python. You know what? That sounds way better. Okay, so now I'm looking at the less nested loop structure. Is this going to give me useful information, any kind of reasonable time frame? Or is it just going to run for 2 weeks and then give me the default dict side effect? Accessing node.children creates empty child nodes if they don't exist, and then accumulate across 2.3 million empty calls. Okay. Cost of one fine number of calls. This is the killer. Look what the recursion does. Each of these two. Okay, for the 5 letters in the word, it descends into a single child because 21 of 26 letters are non-pruning fanouts. Total complexity, that's probably supposed to render into something really cool looking, but it failed. So Python recursion runs maybe 1 million or 10 million calls per second. So this is on the order of hours. So it's completely fucked. My solution has failed. The yellow branch has a misplaced return, likely a bug. Also, I fixed that. Oh, I did not fix that. But that would have actually sped it up. All right, I failed. I have failed once again. Avoid default dict for read-only lookups. Want me to sketch a bucketing approach in more detail? I'm ready to be done with this. This is stupid. Pre-compute each word as a 26-bit letters press. I did that. That doesn't help for yellow and green. Then given a guess, answer pair. The feedback pattern is computable in order 5. Oh. I never should have put the yellow and green into the tree. It's right. Well, I feel like that was my original plan, but then I thought it was going to be problematic. You say, okay, you find everything match. No, 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 no. Because that would give you too many words. Fuck it. All right. Is my strategy of finding number of words possible for each combination and then squaring it a valid way of computing the goodness of a Wordle guess in the first place? If it's not, then the whole exercise is moot. I said or a Wordle guess. I mean, if there were only one output combination and you wanted the lowest possible square number, that would be 1 squared, and you can't get lower than that, then yes, that I think that would be good. And then the worst possible guess, which is not theoretically possible, but if it were theoretically possible that every single word were still in the running and you hadn't ruled anything out, then that would be like what? Some huge number, like over 10,000 squared, which is the highest possible number that you can get. So, yes, your core metric is valid and a well-known one. The exercise is not moot, but the way you're computing the bucket has a correctness bug that means the number you're actually summing isn't a clean partition. Why squaring and summing is a legitimate metric? Model the answer as uniformly random over a candidate set of size n. Partition. Well, no, if it's valid, I know why it's valid. I came up with it originally. A bug that breaks the partition. Your buckets must be disjoint for it missed something. It missed that I pre-computed things which only didn't have repeating letters. So it's not wrong, it just overlooked that detail. That's a mistake that anybody could make. Could I just redo it on letters and ignore the green? I mean, it would be easy. It would be really easy to do this if I just weren't trying to count the greens. Seems pretty dumb. Seems like not counting the greens is actually kind of a problem there. But what if I could choose the best mixture of letters, and then I could do an inefficient way of figuring out which one generates the most greens? Is it possible that it could be a tie? Possibly. All right, fuck off, LLM. Okay. No green node. There is no green node. Fuck your green node. Whole thing was stupid. So all numbers, all numbers, all numbers. Okay. Okay. Fetch vowel combinations count. What the hell am I doing? So we're going to say for W in words unique. We're going to need a bit mask. I can't. I can't be answering a fucking text message conversation while I'm doing this prop. This isn't working. If I ignore her, she's going to get pissed. And this could take me another fucking hour. So fuck this problem. It's just the same thing that happens every time I try to do this. Every single time. Apparently, this problem is harder than I'm giving it credit for, and I just need to accept that.